All right, so good morning. Today we'll be looking at convolutional neural networks. And so convolutional neural networks are especially important because they're a type of architecture, so they're type of neural nets, type of organization of neural nets. And these that are especially used for image processing. So anytime you have to deal with images, you probably want to use convolutional neural nets. And what happens here is that convolutional neural nets really are the defining elements that spark the deep learning revolution. Okay, so they're if you want, the founding father of deep learning. So, as I said, convolutional neural nets, and usually we refer to them as just convnets. Okay, it's easier to say, so I'll just use convnets. Are especially useful for image data. Okay, so this is the main point here. This is the input data. If you have images, you want to use convnets. And the tool they use is they're based on is image convolution. Okay, so image convolution is a way of filtering a picture and to create some kind of filtered version of your picture. Now, this is a well-understood mathematical tool that people have been using for a very long time, way before AI and neural nets. And we know as well that this is a kind of operation that the brain does. So if you look at the visual cortex, which is in between, if you want, the higher level functionalities of your brain and your eyes, well, this part here does a lot of operation, and we know these operations are similar to image filtering by convolution. Some of them we know are related, for instance, to a type of filter called Gabor filters. So convolution gained popularity in the neural net community with Ian LeCun, and so that was in '98. I came up with a network called LeNet5, and this was the first time that people really started to use convolutional neural nets applied to deep learning, and that turned out to be quite successful at recognizing digits in the MNIST database. Okay, so remember the MNIST, we looked at that in one of the early labs. So this is an introductory handout, and we're going to mainly look into the convolution layers, okay, and see how this works. So remember, this is a kind of the summary of the architecture of the type of network we've seen so far. And so you have a layered approach, and in between each layer you have they're called fully connected or dense layers. So in Keras they were called dense layers. And basically what it means is that every single neuron in a layer is connected to all the other neurons in the previous layer. Okay, so if you have say n units in one layer and n units in the other layer, you have n squared connections between all these points. Okay, and obviously the problem is the size of your picture you have. Okay, so I'm just going to skip a few slides here, but on the left here you have your input layer, and this is made of, so each of the circles, the white circles, corresponds to a pixel. Okay, so these are the values of your input vector, and as you can see here, it's actually quite a small picture. It's, I think, 20 by 20 pixels. It's a very tiny picture, and here is represented some of the connections between the next layer and the previous layer. And so we've only done that for 2 pixels. But you can see that each pixel has basically 400 different connections between so this pixel and all the other pixels in the previous image. Okay. Sorry. So obviously this is a lot of connections. Okay, and in fact, the total number of connections you'll have between two layers is the number of pixels squared. Now, if you have, an image, which HD image, which is roughly, say, 2000 by 1000 pixels, so that's 2 million pixels. Now you have 2 million squared connections, so roughly 2 million square weights to train, which is enormous. So this is not practical, and you need to have something a bit smarter. Now, as it turns out, images are very particular data structure, and usually most of the relationship between pixels happens on a very local level. Okay, so you usually more related to the neighbors than you are to pixel far away. So convolutional neural nets work on that hypothesis, and they say that the output, okay, so the treatment you have, sorry about that, the treatment you have on a particular pixel only depends on its neighbors in the picture. Okay, so all these links here corresponds to all the neighbors, and here we looked at a 5 by 5 neighborhood. So we're looking at this particular pixel, and this is the output of that pixel in the next layer. And you can see that we're only looking here at the 25 closest pixels corresponding to that output. And we can do the same for all the other pixels. And obviously, at this point, you realize that, okay, we reduced loads of links, and we have way less weights to train. Okay, so just looking at the neighborhood is key here. Okay, so the idea is like we process pixels, but only on the local level. The second aspect is that when you look at what's going on here, so this pixel here is obtained as the linear combination of all these pixels and times some weights. Okay, so this is weighted by the parameters. Now, these parameters, there is no reason to believe that they should be different here than they should be here. So the second main idea here is that we're not going to try to train separately these weights that we computed for that point from these weights. In fact, we're going to make them identical, and so the technical term for that, we say that the weights are shared across all the pixels. Okay, so this sharing of the weights across all the pixels is another very important aspect. Let's look in this slide. Okay, you have a proper if you want mathematical description of that. I'm not going to go much into detail, but basically remember you have it's a neuron, okay, and here we use a basic definition of it. So you have the two parts. You have the logarithm, and you have the output of the neuron, which is once you have applied the nonlinear activation function to the logarithm. Okay, so remember the logarithm is a linear combination of your inputs, and then you apply the nonlinear activation function to it to get the output. The main point here is that your logarithm only depends on a subsection of your inputs, and that these weights are shared across all the pixels. Let's look at a concrete example. Okay, so here we say that so we look at grayscale images. So a grayscale image means you're only looking at levels of intensity, and that means that because you don't look at color, you only have actually really one channel. So the pixel only has one value, which is the brightness of that particular pixel. So 0 means it's black, and 255 or 1 means it's bright. So why we say here that so this is a kind of a hand designed one. So we say that the logarithm at the next layer is defined by this particular weighted combination of the neighbors. And a convenient way of showing what better way of, instead of having this equation, what you can do is reorganize the weights in a special structure that will follow the structure of the neighborhood. And this is what we get, okay? So we create a little mask, if you want, of all these weights. And that tells us basically that the operation we'll do per pixel is to take -4 times the current pixel plus 1 times, if you want, the sum of these 4 neighbors. So the north neighbor, the west, south, and east neighbor. Okay, so this is exactly the same as here. So we have here minus times 4 the current pixel, and this is your minus times 4 here. Okay, so this representation is a bit more convenient, and basically you show all the values of the weights into a little table, and that shows you what the filter does. So let's apply that to a picture. So here we have a 5 by 5 example. So we have values, the negative, positive, and there's only one channel, so there's just a 2D matrix in this case. Okay. So to produce an output, what we do is we apply this linear combination. So we apply, if you want to overlay the mask of the weights in the particular location you want to compute the output for. So here we're looking at this pixel, okay, and to produce the output, we take 0 times 0 plus 1 times 10 plus 0 times 9 plus, and so on and so forth. And the output of that linear combination is 6. All right, and we can move on to the next pixel and realize that this particular combination gives us 15, and so on and so forth. Okay, and we process the whole picture, and we get values all the way here. Now note that I haven't computed the values on the edge of the frame here, okay? And that is because at this point, to compute, say, the value at the bottom left corner here, I need to access neighbors that will be outside the range, okay? So here, if you look at the neighbor below, well, it is not defined, okay? So it's outside the domain of the picture. So you need to decide what to do at that point, okay? And usually this is specified by, it's called the padding in Keras, okay? And the padding tells us, what to do outside. How do you fetch data outside? And in Keras, you have 2 ways of doing that. The first strategy is to say, to set padding to same. So same means that the output picture will be exactly the same size of your input picture. Okay, so you don't change the size of your picture, and that means that somehow you need to find a value for the pixels that are outside the domain. Okay, so coming back here, if I want to compute this pixel, I need to compute access a pixel that would be, in fact, here that'd be below -4, and I don't know that value. But if I set padding to the same, that means that I will assume that this value is 0. Okay, so we'll assume that all the values that I need to extrapolate, so all the values that will be outside the range of that particular image, will be set to 0. It's a fairly arbitrary decision, but it's a good one because very quickly you'll find that most of your activation maps are mostly zeros, and with some values not 0. So 0 is probably actually a fairly common value, and it's a good value for extrapolation. The other approach is to take a more safer approach, okay, and to say, well, if I have to extrapolate a value, if I need to invent a value, then I just don't compute. I just stop the computation right there. And so valid means that basically you stop there. So if you do valid, then you will you will essentially not compute the values here and just process the picture and just have a smaller picture. Okay, so you start with a 5 by 5 image, and now you have a 3 by 3 image. And you just crop and remove the edge of the picture. Now this doesn't really matter if you have a very large image, and if you crop a few pixels here and there, it doesn't really matter. But if your picture becomes smaller, then just keep track of that and just keep that in mind, that maybe your picture will become dangerously small. Okay. So we've seen two things. So we've seen convolutional layers, and we've seen how the padding involve that. Okay. So this is an example of what happens. So you have your input image, which is the bird here, and this is made of 3 layers. Okay, so these are actually the red channel, green channel, and blue channel of your input image. And when you combine that, into a color picture, then you get color. But really deep down, each of these channel is just a grayscale channel. Okay, so dark value here means you don't have a lot of blue, and bright value here means you have a lot of green. Okay, so a convolution layer, say if you can produce, say here, 6 different filtered version of this input, and applied with convolution, and this is, say, typical results of what you might get. Okay. So if you look at more detailed example, this is what you will get in Keras. So you define your input, which is a picture of size. Actually, this picture of the bird is 443 in width, 592 in height, and you have 3 color channels. So you have 3 channels as well for the last dimension. And then we feed that into a convolution layer, and it's called conv2d in Keras. And basically, the first number tells us the number of filters we're going to define. So here we're going to define 6 filters. So we're going to create 6 new versions of that picture. And the convolution, the neighborhood size, so the kernel, if you want, it will be of size 5 by 5. Okay, so that means we are only going to, all the outputs of these filters will be based on a linear combination of 25 neighbors, so 5 by 5 on the images of size 5 by 5. We can specify as well the activation function. So here we just say it's a ReLU, and we set the padding size to valids. Okay. Now let's look at what's happening when you do that. So the output size, because we set valids, will be slightly smaller. Okay, and basically because the size 5 by 5 means that we are going to strip out 2 pixels on each side of each of the sides of the picture. So that means that the width of the picture is going to go down from 443 to 439. Okay, so we lose 4 pixels on the x direction on the width. Okay, and same for the height, we're going to lose 4 pixels as well. Okay, so the output of this is, if you want, it's a new picture of size slightly smaller than what we started from, and that's because we set the padding to valid, and then we get 6 channels out of that. Okay. Interestingly, here the number of weights is not that high. Okay, so let's look at how many weights are defined by a particular filter. Well, because you have a neighborhood of 5 by 5, and you only have really, say, 25 or potentially actually 26 weights. I say 26 because I didn't include here the bias, okay, the W0. But let's say it's 5 by 5, okay, and then it's 25 parameters to train. Now we define 6 of these filters, and so that's 6 by this number. And I forgot to mention that we have 3 color channels. So actually the convolution involves not 5 by 5, but 5 by 5 by 3 weights, okay? And in total, that's only 450 weights to train, which is only a fraction that what we required in a dense layer. Remember, in a dense layer, we'll be looking at something of the order of a few billions for this particular picture, okay? So it's a massive reduction in number of parameters you have to deal with. So that's it's really a great effort, okay? The second aspect to keep in mind, so that's it for convolution filters, convolutional layers. So we reduce a lot the number of parameters to train, but there's one thing we haven't reduced is the number of units in your network. And that is because when you do convolution, say you have a picture of size 2000 by 2000 by 3, so that creates around 1000 weights. If you have a 5 by 5 convolution filter and you create 16 filters, okay? But the number of units you have is still basically the size of the output image. So the output image would be, in this case, say 2000, roughly 2000 by 2000 by 16. So you still have 64 million values to deal with, okay? And that's still a lot of units in your graph. So usually you want to reduce that to just a few hundred or maybe a few thousand units. And that's because you still want at some point to use classification, for instance, or you still want to use these units for something. So there's two strategies for doing that. And by the way, what we're doing here is simply we have images, okay, so think about that, okay, so at each stage of your convolution, you produce an image, and with various amount of channels and different size. And what we're looking at here is resizing the pictures, okay? We're trying to find operation that could try to change the resolution going from 2000 by 2000 to something a bit smaller. And so there's two options available. There's you can play with a stride, or we can play with it's called pooling. It's a particular layer that will do basically the downsampling of the picture. So sorry. So let's look at stride. Okay, so here your picture is of size 16 by 16. So all the white dots on the grid here, the white squares on the grid correspond to your input pixels. And in blue, I showed the pixels that are actually processed, okay? And here I set the stride to 2. That means that I'm only going to process every second pixel on the X and on the Y axis, okay? So we left out, So we left out quite a lot of pixels, and we start with a 16 by 16 image, but at the end of the process, we only end up on the next layer with a 7 by 7 picture. Okay, so we're leaving out a lot of the computation and the number of units we have. Okay, so we can go further. If you increase the stride to 3, then it's every third pixel in X and every third pixel in Y, and basically here we only process like every 9 pixels actually of the picture. And you can go even further, okay? So stride is something you called, if you look at that, it's something you call directly as part of the convolution. Okay, so you reduce the amount of computation there. What you can do as well is apply, it's a slightly different approach, okay? So you can add a separate layer where you say, okay, this layer is just in charge of the resizing of the picture. And we call that pooling. And there's different strategies available, okay? So one which is quite popular, it's called maxpooling. And so here on the left, you start with a 4x4 picture, okay? And in this 4x4 picture, we decide to try to downsample it by 2. Okay, so the keras function for that is called maxpooling 2D. And we define here the size of that pooling, and 2 by 2 means we're going to reduce by half the size of the picture. And so what maxpooling does is like it defines these little blocks 2 by 2, and you are going to only pick the maximum value. Okay, so you're going to pick 10, for instance, in this green block. You can pick up 9 in this yellow block, and so on. Okay, and so the values you've picked up here are just maximum values of these blocks. So why do you want to take the maximum values? Well, remember, most of the activation functions you're dealing with produce only positive numbers. Okay, so you take ReLU, for instance, or the sigmoid, the output is always positive. And usually in neural nets, so when you have neuron units, the meaning you have from the interpretation you can have from the values is that if the output has a high value for a particular neuron, that means that the feature is important for that. The feature associated with that neuron is activated. Okay, so it means you detected something about that feature. And if it's set to 0, it means like nothing has been detected. It's a rough explanation, but basically in most of neuron type units, this is what the behavior you have. So the higher the value, the more it says that this feature is present in the data. And so here what we want to do is to be able to downsample the picture while still picking up. You don't want to miss out on these high values. If you have a high value here, this tends means that that particular filter picked up on something, so you want to carry on that high detection into the next level. Okay? So anyway, max pooling, it's a way of reducing the size of your picture by just picking up the max values. Okay? You can do different strategies of pooling. So one of those is average pooling, where basically you don't take the max, but you take the average of the values in your block. So there will be a more typical downsampling operation. And there's another one called stochastic pooling, which I don't think you have in keras, but basically you take a random value in the field here and just report that. Okay, so this is kind of typical code for convolutional neural nets, and this is what you have in keras, but the typical structure you have in other libraries. So you start from your picture. Here's 32 by 32 pictures in color. So you have three channels here. You apply convolution of masks 5 by 5, and you can create 16 of define 16 of the filters for which you're going to have to define the weights. Okay, and you specify an activation function for all these filters, and you have to set a padding strategy. So define how you deal with neighbors that are for boundary pixels. And then you have to decide the stride, and here I decide to use all the pixels. And then you follow that up with a downsampling operation, which here choose max pooling of size 2 by 2, so means that we're going to reduce the resolution. Okay, so the input picture is of size 32 by 32 by 3, and I'm going to create, the convolutional layer is going to create a new picture of size 32 by 32 by 16. So because we defined 16 filters, and then we're going to do a max pooling operation, which is going to reduce the size of the output to 16 by 16 by 16. Okay. So let's look at different architectures, and I'll be looking here mainly at conv nets, so convolutional neural nets applied for image classification. But these are common ideas for most neural nets applications, okay, for images. So you start from your picture, which is potentially high resolution. And then you're going to start doing a number of convolutions. So you have a convolution layer here, and you're going to create a number of feature maps. Okay, so a number of filtered versions. So in this case, you have 4 different filtered versions of that picture. And these are high resolution. These are the same resolution, same size of your input image. So you will follow that by some subsampling operation so that your picture is smaller, and you will add more convolution to create more and more of the features, and you're going to then again downsample that to make the picture smaller, and you have at the end of that process, that convnet, what you have is basically quite a small picture, typically of size, say 10 by 10, 5 by 5, something quite small, but you have loads of layers here. Loads of, it's called depth, but it's a bit misleading term, but basically you have loads of channels, okay? So you have loads of features created for each of the pixels. So I say that again, you have a small picture, maybe 7 by 7 pixels, but each of these pixels has many channels, okay? And each of the channels, each of the values corresponds to, if you want, a feature, particular feature for that channel. And then when we reach a point where the picture is so small that the premise of convolutional neural nets, which is about neighborhood size and the fact that your pictures are big and so on, doesn't work anymore. So basically, at this point, the picture is so small that you can't really say it's a picture anymore. And so you might as well just, at this point, so you have a few thousand units, to consider these units just as a single vector, and to feed that into densely connected way to other layers. Okay. So basically, you have 2 parts, well, actually 3 parts in the network. Okay. So you have the first part, which is the convolutional neural nets, and we have interleaving of convolution followed by some pooling operation, and convolution, pooling, convolution, pooling, convolution. You reach a point where the picture is so small that it doesn't make sense to keep on doing convolution. And so what you do instead is that you feed that into dense layers. Okay, so here at this point you use normal feed-forward networks we've been looking at, and then you finish by, if you do classification, you finish that by a softmax or something like that. So I'll just show you one example. Okay, this is called the VGG16 network, and I'll come back to that, but I just want to show you what the code of this network looks like in Chaos. So you start at the beginning here, and you have 2 convolution back to back, where you create images of size 64 channels, and you see the kernel size you use is quite small. Okay, so you do small convolution using a small neighborhood of 3 by 3, and at the end of this operation, you do max pooling. So it means that you downsample the resolution by half. And then you feed that into you build more features, okay? And you have now 128 channels. And you do 2 convolutions, and then you downsample again. And then at this point, you have build up 256 filters, okay? So you have 256 channels. And then you do that multiple times, and then you downsample again. And you keep on doing that. And what we're doing here is like we're building up. So we started from 3 color channels, and now we have 512 different features computed, and 512 per pixel. But the thing is, at this point, the image size is quite small. Okay, it's a very small image size. And what we do here is we feed that into dense layers. Okay, so going from a 2D structure to more just 1D or dense structures use the flatten operation in Keras. but that doesn't really matter. What matters is here you have two dense layer back to back, and you see that the number of units you have is quite small. I mean, it's still quite high, but it's 4,000. Okay, so it means that you start from a picture potentially of size quite high. You know, it could be 2,000 by 2,000 picture, and you end up with a very small number of units. Okay, so you say somehow you compressed, you represented the entirety of the picture, which had millions of values, into only 4,000, a feature vector of 40,000 values. So anyway, so you have two dense layers back to back, and it's followed by a you finish by a softmax operation. Okay, and the softmax operation, as you've seen, allows you to do the prediction. So let's look. All that is typical of all the network architecture, starting from LeNet 5. Okay, so this is the pioneer. Okay, so this is the original ConvNet by Jan LeCun in '98. So remember, we're trying to look at digits or letters, and we have a small input size, very tiny picture size expected, so 32 by 32, and you build up. So you have four different convolution steps, and each step we try to reduce the picture size even further to a point where the picture size is only 5 by 5. It's very tiny, but each of the pixels have 16 features computed for those. Okay, and at that point you flatten all that, and you just say, okay, this is a whole just one vector, and you follow that by a number of dense layers and finish your classification at the end. This is AlexNet. So AlexNet is really the network that you can safely say this is the paper that studied the deep learning revolution, and so that was the winning entry for the ILS VRC 2012 competition, which is basically a competition. So I talked about this one. It's a competition where they have millions of pictures with thousands of classes. You have to say, and the aim is given a picture, you say whether it's a dog or a snake or what type of snake it is and so on. So you have to classify and you have to name the object on the picture. And this is a structure, the network they've used. Okay, so you start with so each of the blocks here corresponds to convolution steps, and in the first one they build up 96 features, and they create a picture size of widths and heights of 55 by 55, and then they do a number of convolutions and they increase the depth here of each of the pictures. So you build up more and more features. So you go from 96 to 256 to 384 and so on. But the picture becomes smaller and smaller. Okay, so you start from 55 to go all the way down to 13 by 13. And at this point, it feeds into this what's called FC, which stands for fully connected layers. So that's your dense layer, okay? Using the dense layers, we've seen them. Okay, and you end up with this last layer as 1,000 because you have 1,000 classes to decide from. So you see that this network is not that much different from the original LeNet 5, and it's similar, but maybe with more. You have more filters generated, basically. And this is the VGNet as we've seen it in the code. So that's the same as this code here. And so basically, you start and you create more and more layers, and you see you all the way here to the last convolution. So from here to here, this is convolution. The last convolution layer in the last block, basically you have 12 channels generated, The pixel size is only 14 by 14, which is again not very big. And then at this point, that is followed by 3 dense layers or 3 fully fully connected layers. Sorry, and you finish by softmax. And this was actually the winning entry for the 2004 competition for object recognition. And it's quite a popular network. You can find the weights are already trained, and you can find them, download them online, and you can actually, it's quite easy to just reuse that network for your own work. Okay, so this is kind of the, it's an introduction, okay? So these are the building elements of convolutional neural nets, okay? So when we talk about conv nets, usually these are the 2 main tools we have. So we have the convolution layer, and we have some pooling layers as well. So let's try to visualize what's going on here. And one of the main problems you have with neural nets, and still an upfront problem, is you train these networks, but very hard to interpret exactly what was trained and what does a particular neuron. The good thing with conv nets is that you work with pictures, and therefore it is somehow easier to visualize what is the effect of a particular filter. So what we're looking at here is a particular technique to do that. There's different techniques, okay, for visualization. There's been a number of papers in the recent years, but what we'll be looking at today is a technique I particularly like, and that you can find on the Keras blog website, actually, and you can have the code for that as well. So what we're trying to do here is to say we're going to pick up a particular filter. Okay, so we're going to look at a particular filter in. So we're going to look at a specific filter in your network. Okay, and at each layer you produce a number of filters, and we're going to look at one of these filters. And what we're trying to do now is to engineer an input image, so an input image to the entire system that would somehow maximize, so that's the input image, and we're going to maximize the activation for that specific filter. So remember what I said, okay? So the kind of meaning of the activation is that if there's a high activation, if the value coming out of the filter is high, means that this filter has detected something with a high value, okay? And so what we want to do here is to find an image that's going to create, where the output of the filter is going to be very high, the maximum possible value, okay? And the idea is like, okay, say if a filter detects a dog, okay, then we want to engineer an image that will maximize this dog-like detection, okay? So we want to create an image where the dog detector will be high, okay? So say that again, we're trying to create a picture that would maximize the activation for that layer. And the way we do that is, it's actually quite simple, and we have all the toolkit to do this already. So we define a loss function, something we want to optimize, and this loss function is basically the mean value for the activation for that filter. Okay, so we want to say we want to maximize the activation for that filter, so the loss function is just the average value for that filter. And the question is, we have a loss function, but we need to have, we're going to use a gradient descent operation, and so we need to compute the gradient. Well, as it turns out, we know how to compute the gradient. It's, you just use backpropagation. So we use backprop to compute the gradient, but here we don't try to change the weights, okay? So the weights are already set. What we try to change is the input image. So what we compute is the gradient of the loss function, but with respect to the input image. Okay, so we said our parameters now is the input image, and we're trying to optimize for the input image. But still, the mechanism for that, to solve for that, is backpropagation, which we know how to do. So once we have that, so we have a mechanism, so we can start from a initial picture, so say a noisy picture, like just 0, okay, we start with 0, and we evaluate, the whole network up to that filter, and we look at the mean value for the activation filter, we look at the gradient, and respect to the input image, and then we update the input image using that gradient. Of course, here we want to do is to maximize loss function, so we want to maximize the activation. So instead of a gradient descent, which is used for minimization, we use a gradient ascent, which is for maximization. And you keep on going, okay? So you update your picture, use the gradient of that picture, you update it, and so on. Anyway, these are some of the examples of what these engineered images looks like. So Conv11 is, if you come back at the code, it's your first layer, okay? It's called block 1, Conv1. So that's the output of this first convolution. So you have your input image and you have the first convolution. You create 64 of these filters. And what we're looking here at is the images that maximize a few of your 64 filters, okay? As you can see, so these are the input images, and they really correspond to low-level features, okay? So you have some texture if you want, and these textures will be nicely picked up by every single specific filter. You can see each filter has different design, they're quite different, and they will pick up different types of texture. So if you look at Conv21, so you're after a few convolution, the next block of convolution, so you have more filters here, and the filters here pick up different types of texture, slightly more complex maybe. And as you go deeper, so you look at Conv41, which is almost the last layer, you can start to see quite complex patterns happening, okay? So some of these images, each of these images corresponds to the images that maximize the output of a particular filter, and you can see that basically these filters are in charge, if you want, of picking up textures that look like these patterns, okay? And this is the last layer of the VGG16. As you can see, the patterns you start to get are fairly complex, okay? And if you want to interpret that somehow, kind of in a hand-wavy way, these are kind of form a basis of images that you use. You say, I'm going to be able to, if my object is a combination of these images, then I will be able to, pick up which of these filters I should use to best match a particular object. So you could say a dog is a bit of this filter and this filter and this filter, and you combine that together. It's a bit hard to interpret, but basically it's interesting to see that these, as you go deeper in the network, you really start to develop features that are quite complex, okay? Each of these features are quite complex, correspond to quite complex patterns. And so as deeper you go, the more complex the features can be. All right, so we've seen the basic element of convolutional neural nets. And we see that they're very effective because there's so far you can go with dense nets, okay? Using fully connected layers, it's complicated, you have way too many weights to deal with. Whereas with conv nets, it can really reduce the number of parameters. Now, of course, conv nets only work for pictures, okay? And this is, the limitation, but there's a lot of applications where picture work. I mean, even if you work on, say, audio processing, if you look at the spectrogram of your sound, you could consider that as being images, and it still works. So the range of application is actually quite wide, and this is what so much powerful that basically ConvNet was, you can say ConvNet was really the start of the deep learning revolution. So a last point is convolutions is nothing new. Okay, so when you look at convolutions, this is something that people have been doing for many years. What is new in ConvNets, okay, is that now we have a framework for systematically train what are the best filters. Okay, so what VGG16 has done is design a basis of filters that are really powerful at explaining all sorts of images you can have. Okay, this is a kind of filters that would have been too hard to tailor by hand, or to try to design yourself by hand. And now with neural net, you have a way of really designing all these filters in an automated way, in a very powerful way. All right, this is it. Thank you.